Hi, welcome to Drafting 110, Print Reading for Drafters. My name is Anne-Marie Harden. I will be your guide through this course. We're going to move into Chapter 5 today, which is all about joint design. What we're going to do here is we're going to explain the significance of mechanical properties of materials in welding. We're going to talk about 5 different types of stress. And that is really not the overriding urge to strangle somebody whom society says you cannot strangle. That's something different. We're going to talk about some common terms that are associated with stress and strain and deformation. And that'll make more sense as we get there. And we are also going to list some common mechanical properties of metals. We've got a few more things we're going to accomplish in this chapter. We're going to identify the physical properties of a metal and why we care about that in welding. We're going to describe some types of chemical reactivity of a metal. And I know that this is a print reading for welders class and not a welding class, but sometimes even if you're a drafter creating the drawings and not necessarily a welder, you need to understand all of this stuff, especially the reactivity, because sometimes you are a part of the checking process, the quality control. So it's good to be aware of these things. We're going to list different types of loads and talk about the things that we need to consider when we are selecting a weld joint. We're also going to list some basic rules for maximizing weld strength. And we're going to discuss the importance of welding position, weld joint access, and welding location. All right, about the 5 types of stress. I said this is not the only acceptable. Stress is really a normalized way of talking about the loads that a member in a structure has to carry. So every machine part and every structural member is designed to safely withstand a certain amount of stress. And there are different types of stress, and that the type of stress is determined by the position and location of the member. Tensile stresses. You can envision this as a member being pulled on, kind of like pulling on a rubber band, putting it in tension, pulling it apart. Compressive is compressing, so you're pushing. The member is holding something apart. You're pushing in on the ends, and that's compressive stress. You get shearing stress here when you've got 2 members that are either 2 parts of a member or 2 members that are attached together, but then you slide, you've got some attempt to slide one against the other. And you've got bending stress. That's exactly what you think. You've got a long span, and that's to flex and bend. And then you've got torsional stress, which is like a ringing motion. So this torsional stress occurs when you've got a shaft in a rotating application. Let's talk a little bit more about tensile stress. Now, stress, as I said, is a normalized way of talking about the force applied to a member. So stress is the force divided by the area over which that force is applied. So in this schematic here, the force is the force that's applied to each end, and because of the physics of this unit, that the forces are equal on both ends, and the area is the cross-sectional area of the member. So if you've got a 12,000-pound force being applied to a piece of flat stock with a cross-sectional area of 0.75 square inches, you take your force, you divide it by the area, and you get a stress of 16,000 pounds per square inch, or PSI. Now, if we stretch a member far enough to the point that it starts to deform, we will get a neck here in the middle, because as things stretch longer, they get skinnier in cross section, like a rubber band. Since we're making the area smaller, that means that we've increased the stress, even if we don't increase the force. And so now let's talk about compressive stress. Compressive stress works just the way, except that it's just exactly the same, except that instead of pulling, we are pushing. So your compressive stress is your force divided by your area. That is, your force is equal on both ends. Your object is compressed and it gets fatter. Because think about your favorite cubicle gum or candy, juicy or not juicy, but bubblicious, or the little square toffee things, or even a soft eraser. When you squeeze it, or a hacky sack works great for this too. When you squeeze it, it gets fatter. So our area increases as our force increases. Shearing stress is caused by two equal and parallel forces that are acting on an object from opposite directions and that are not aligned. So we've got a pushing force on the top and a pushing force on the bottom. Or we could have pulling forces on top and pulling forces on the bottom. Shear stress is still equal to force divided by area. The difference here is the area, the area is still the cross-sectional area. This definition changes in some textbooks, so pardon my stumble there. So the shearing force is the force divided by the area, and you take your 40,000 pounds applied force and you divide it by 0.75 square inch area, you get a shearing force of 53,000 pounds per square inch. Okay, bending is a little more complex, but not too bad. The bending stress is equal to the maximum bending moment in inch-pounds. And now this is a engineering thing, and we're not going to worry about what it is. It will be given to you if you ever have to do this calculation. C is a distance, and it's the distance from the neutral axis to the farthest point in cross-section. What that means is, if we look at how this beam bends, if we look right up here, this line has gotten a little bit shorter than what we started with. The top part, as the beam bends downward, the top fibers get compressed. They get a little shorter. The bottom fibers get stretched. They get a little longer. So somewhere in between the top and the bottom, there's a plane, a line we can draw, where this length of the bent object is exactly the same as the length what we start with. That's called the neutral plane. For most beams, the neutral plane is going to be in the middle. C is another one of those things that will be given to you in this class. You don't have to find C. That's an engineering problem. And Z is what we call a section modulus. And again, that's an engineering term that you will not have to find or understand. Just understand that what these things mean in this equation. So the bending stress, M, is the maximum bending moment. C is the distance from the neutral axis to the farthest point in the cross-section that will be given to you. Z is the section modulus, and that will be given to you. So we plug all of these things in. We're told that we've got a 1 square inch solid shaft with a bend of 1,200 pounds M. From the neutral axis to the cross-sectional axis, or cross-sectional area, C is 3/4 of an inch. And we're told the section modulus, that's C, is 0.053. We plug those in, we crunch through our calculators, and we get a bend of 16,981 or 17,000 psi. Torsional stress is twisting stress, and the other word for torsional stress is torque. And depending on your background, you may be familiar with torque. It's just the pounds in force times the distance L. So if we've got, what is the torque of a 240-pound force applied over a distance of 16 inches? Just multiply those two numbers together to get the torsional stress or the torque. Okay. Now, one of the reasons we wanted to explain this to you is because we talk about material properties in terms of stress-strain diagrams. We're going to talk about a couple of different things about this diagram. The first is what we call elastic deformation. And if you look right here at the beginning of the stress-strain diagram, this is a straight line. What that means is that the stress or load is proportional to the strain or the elongation of the material. And here in this early region where this line is straight and those two are proportional to one another, that deformation is elastic, meaning it goes away. If we unload the material, if we take the load off, the material will be its original shape and length and size. If, however, we go beyond a certain point, and that point is the yield point, we get into the plastic deformation range. And the plastic deformation is permanent. It's like sticking your thumb in putty, that never goes away. And so that we call that the plastic deformation range. And then eventually we can load the material up to the point where it breaks. That's fracture. The modulus of elasticity is a very important material property in material design or material selection and structure design. The modulus of elasticity is only valid in the elastic region. That first part of that stress-strain diagram we looked at a minute ago. And the modulus of elasticity relates the stress, the normalized load, to the strain, the deformation, the how much longer the thing gets. And we can look up E's, moduli of elasticity, for different materials. So this is a material property. And it's really handy because what it does is it allows us to think about, if I put a certain load on a piece of steel, what's that going to do to the dimensions of that steel? How much is my steel cable going to stretch if I hang 1,000 pounds from it? And so the way we use that is if we're given stress and strain, we just use the relationship that the modulus of elasticity is equal to the stress divided by the strain. And we're given a modulus of elasticity, or asked, what is the modulus of elasticity of a 1-inch square piece of metal subjected to 30,000 pounds of tension and exhibiting 0.001 inch per inch. So strain is unitless, it's in inches per inch. So first thing we have to do is figure out our stress. Stress is the force divided by the area. This is a 1 inch square, which means it's an inch by an inch, so its area is 1 square inch. 30 pounds is applied over that 1 square inch, so the stress is 30,000 pounds divided by 1 square inch, or 30,000 pounds per square inch. So this 30,000 is the stress. They give us the strain, so we divide that stress by the strain, and we get a modulus of elasticity of 30 million psi. The modulus of elasticity is an indicator of how much stress is required to deform a metal or another material, a given amount. We also have to worry about thermal expansion. As things get hotter, they get longer. As they get colder, they get shorter. This is why railroad rails are not laid tight end to end. You have to allow space for them to expand in the heat and contract in the winter. And again, we can predict how much that change is going to be based on the coefficient of thermal expansion. That's what C is in this equation right here. And so our coefficient of thermal expansion is equal to our length differential, our change in length per degree Fahrenheit. So this is, we take our change in length and we divide it by the change in temperature that caused that change in length. So if we've got an 8-inch wrought iron bar that increased to 8.0000661 inches, when the temperature increased from 68 degrees Fahrenheit to 78 degrees Fahrenheit, what is the coefficient of thermal expansion? So we just take those numbers and we plug them in. The change in length is the final length minus the starting length. That's where the 0.000661 comes from. The change in temperature is the final temperature minus the starting temperature, or 10. And we find the coefficient of thermal expansion. Now it's more usual to look up the coefficient of thermal expansion and the modulus of elasticity for materials, and then use that to predict the changes, either the stress or the strain or the change in length due to temperature. But here you can see how those properties are determined. All right, let's shift gears a little bit and talk about types of load. A load is nothing more than an external force applied to an elastic body. Elastic body just means pretty much any material that doesn't sink under that load. Applying this load causes stress in the material. Now we can talk about different types of stress, or different types of load. A static load is a load that is applied gently and smoothly and stays constant. An impact load is a load that is applied suddenly and or intermittently. An example of a static load is the weight of a building on its foundation. That is a static load. An impact load is, well, for example, the impact of a jackhammer on concrete. Now that's usually a destructive load. But you can think of other impact loads. Walking, the force of people walking on a bridge or on an overpass is an impact load. A punch, if you've got a piece of machinery that is punching or stamping, that will create an impact load on whatever the working surface is. And you can have a variable load where load just varies over time. An example of that might be vehicles on a roadway or vehicles on a bridge. Not really an impact load because it's not really sudden, but it's not really a static load because it changes. The different types of loads can impact how a material behaves or responds. So when we talk about how a material is going to respond to load, we need to think not only about the amount of load, but also the type of load. So there are 5 basic weld joints that we use with applicable weld types to meet load requirements. These basic weld joints are the butt, the lap, the T, edge, and corner weld joint. And those are shown across the top of your table here. And this table is found in your textbook as well as on this presentation. Each of these joint types may be used with different weld types to meet load requirements. Load requirements will dictate the strength of the required welds. What we should say there is that load requirements will dictate the required strength of the weld. And there are some things we can do to maximize weld strength. Notice first that not all welds use weld joints, so do be aware of that. But here are the things we can do to maximize weld strength. We want to minimize edge preparation. So we want to minimize the amount of work we do to an edge because that reduces cutting and machining costs. We can provide good weld access. Allowing access to a weld by welding equipment will make for a better weld. But you have to think about what equipment you have available. If we minimize the filler material required, that's a good thing because minimizing filler metal not only increases strength, but it also reduces the cost of the weld. For example, a 3/8 inch fillet requires 44% more filler metal than a 5/16 inch fillet, but only provides 20% more strength. So there's a balancing act there. We want to reduce excess heat. Reducing excess heat applied to the weld area during the welding process minimizes molecular changes of the base metal and the fillet metal. And those molecular changes can impact the strength. We want to minimize the number of welds. A weld is a very strong type of joint, but it's still a joint, and original material is still probably going to be better. So minimizing the number of welds reduces the filler metal required. And distortion of joint members from the heat applied is also reduced if we reduce the number of welds. We want to size our weld for the thinnest joint member. So the size of the weld should not exceed the size of the thinnest member that is a part of this joint. There are 4 basic welding positions, and they are depicted here: flat, horizontal, vertical, and overhead. And gravity can impact the performance of a weld. So in horizontal, vertical, and overhead positions, gravity reduces penetration and filler metal control. This can cause weld defects and result in weak welds. Smaller parts can be placed in the flat position for efficiency. Always more efficient to weld flat. But some large parts cannot be moved and positioned for flat welding, and they have to be welded in positions that are not as advantageous, and we just have to take that into account. Proper fit up always is a good idea. Proper fit up assures that joint members are in the correct alignment and have correct edge preparation, and the required root opening for proper penetration and sufficient weld reinforcement. Sub-assemblies can eliminate some access problems. So sometimes you build some portions of the piece separately before you then insert those parts into their final position. The thing we need to keep in mind is that welding performed in the field is impacted by weather. Often, field welding results in a decrease in welding productivity because of ambient temperature, weather, welding conditions, reduced welder efficiency. For example, pipe welding of sections of pipe used for the transmission of water, chemicals, petroleum products, other materials across great distances has to be done in the field. We have no alternative. The pipeline right-of-way must be cut and graded for access by the pipe laying and welding equipment. The ditch is dug, the joints are strung for fit-up and welding. The sections of the pipe are lined up and welded in place to the required specifications. This activity actually requires highly skilled welders to work quickly in sometimes pretty uncomfortable conditions without compromising weld quality. So a quick review, things for you to think about and make sure you know the answers to. What is a mechanical property? List the 5 types of stress. What is a chemical property? List the 5 types of loads, and what is the difference between a primary weld and secondary weld? And the answers to all of those questions can be found in your text. So read this chapter and then take the associated quiz. Have a good day. We'll see you again soon.